Hello and welcome to the lecture series on reinforcement learning. My name is Alireza Modirshanechi, and this is the third and the last part of our lecture on curiosity-driven exploration. In the first part of the lecture, I talked about exploration bonus in tabular reinforcement learning and how it can help agents to collect rewards in multi-arm bandit task and Markov decision processes. In the second part of the lecture, I discuss about the general notion of curiosity-driven reinforcement learning, even when there is no reward, and how surprise and novelty can be implemented in deep reinforcement learning, and there are benefits in auto games and in navigation tasks. In the third part, we are going to go beyond the benefits of intrinsic motivation and talk about some of its drawbacks, and in particular the noisy TV problem. The noisy TV problem is essentially about the situation of being curious in the presence of stochasticity. Before going to details, let's start with this particular example. The example is from the same paper that I presented in the last lecture, Burda et al. In ICLR 2019, the same paper that applied a surprise-seeking algorithm to multiple Atari games and showed that by only seeking surprise and without any notion of extrinsic reward, the agent could collect extrinsic reward. Here, this is another experiment that they did for 2D navigation with visual inputs. Let's look at this video. This is a summary of their task. The agent received visual input, as you can see here, and should navigate in this environment. The goal of agent is to find the goal state by moving here, and the goal state, you can see it in the next turn here. This is the goal state, and when the agent finds this goal state, it receives a reward. What the authors show is that in this curve, you see on the x-axis millions of frames of training, and on the y-axis extrinsic reward per episode. The gray curve that you don't see, because it's always 0, is if the network, if the agent was only driven by extrinsic reward, and as you can see, it never finds the goal state. But the other two curves are surprise seeking with two different feature space. One is with random CNN, and the other one is with inverse dynamic features that I introduced and discussed in the previous lecture. And you can see that surprise seeking is very successful in solving this task and finding the goal states after 6 million frames. Almost immediately, the agent goes to the goal states. But the authors do something very fun. Let's look at this other video. The agent again moving the environment. And here, the main difference with the previous case is that the author added the TV to one of the walls in the environment. Now the agent can stay here, look at the TV screen, and one of the action, let agent change the channel on this TV. And after each time that the agent take this action, a random image appear on the screen. So it is not predictable, and because it's not predictable, it always has a high surprise. And what authors show is that here, these two curves is what you show before, is surprise seeking when there is no TV, and these two other curves are the same as before, but when the TV is added. And as soon as you add the TV, we see that the surprise seeking gets stuck here, as you are seeing in this video, and never leave this TV screen. You can see here that the surprise seeking had found the goal state. So it knows that where the goal state is, but it is so attracted to this random TV that it does not leave it, and it does not go to the goal state again. And this is a well-known problem in reinforcement learning, that curiosity-driven agents can get distracted by unstructured stochasticity. However, seeking different intrinsic reward signals results in different levels of distraction. In particular, it is well known that seeking information gain is believed to be better than seeking surprise. And this example here is an extreme case of seeking surprise that that the agent is completely distracted by the noisy TV. Before going forward and discussing about solutions to noisy TV problem in deep reinforcement learning, let's take a detour and talk about information gain and surprise in general, and gain some intuition that why information gain seeking is better than surprise seeking in the presence of stochasticity. Let's consider this transition from state action pair ST and AT to state ST plus 1. As we saw, transition surprise for this transition is defined as some measure of how unpredictable ST plus 1 is conditioned on ST and AT. The example that we saw was Shannon surprise or surprisal, that is defined as minus logarithm of the estimated transition probability from ST and AT to ST plus 1. So the less likely this transition, the more surprising it is. Another definition is a state prediction error, is simply 1 minus this transition probability. Very similar to the Shannon surprise, but now instead of being logarithmically decreasing with the probability, is linearly decreasing with probability. Both saying the less likely transitions are more surprising. Another definition is the squared error. This is the same as the one that was used in intrinsic curiosity module of Pathak et al. In ICML 2017. It's basically the difference between the next state and the predicted next state based on the current state action pair, where I now use ST plus 1, but I could equivalently use phi of ST plus 1. There are many different definitions of surprise. In this paper in the Journal of Mathematical Psychology, we discuss 18 different definitions of surprise and they're linked to each other. But I'm not going to discuss the details of those. We limit ourselves to these 3 definitions for today. On the other hand, information gain refers to many different quantities in different contexts. One way to unify many of the definitions of information gain is by considering a general distance between the 2 distributions PT and PT plus 1, where PT is computed before, is the estimate of agent before observing ST plus 1, and this one is after observing ST plus 1. So upon observation of ST plus 1, the agent updates its estimate, and information gain measure the distance between these 2, or in other words, how much the agent gained knowledge or information upon this transition. One of the ways that one can define this distance is based on Kullback-Leibler divergence. It's not a proper distance because it's not symmetric, but it's commonly used in the literature for measuring the difference between PT and PT plus 1. This information gain is also known as postictive surprise, and it is discussed again. This manuscript is linked to the other definition of surprise. Another way that one can define information gain is based on using L1 norm for D, which basically says that for every state S prime, let's compute the difference in this probability and sum over all possible state S prime. This is closely linked to the total variation distance if you're familiar with, but we are not going to need all the specific property of the total variation distance for today. In the next slide, I'm going to focus on this definition of information gain and this definition of surprise because they're simple, and try to give you some intuition about why information gain seeking is better than surprise seeking in the presence of stochasticity. To answer the question, let's consider the simple exercise that you have in week 13. There you analyze, you compare information gain with surprise and the number of observations. For the surprise, you consider the state prediction error, and for information gain, you consider the L1 norm difference, which is also equivalent to the total variation distance. It's the sum of this guy. You see something beautiful there. that in a very simple setup, the information gain converges to 0 as time goes to infinity, independently of the level of stochasticity in the environment. So no matter if the environment is stochastic or not, as time goes on and the agents collect experience and interact with the environment, this term, the information gain, goes to 0. And the reason is basically because both of these converge to the same distribution, and if you are using the true family of world model, they both converge to the true distribution of the environment. However, what you see is that average surprise converges to a constant as t goes to infinity, and importantly, this constant increases by increasing the stochasticity in the environment. So average surprise in the limit depends on the stochasticity of environments, while information gain goes to 0. The important thing is that because information gain goes to 0, no matter if you have a stochasticity or not, watching the TV after a while becomes informationless and the agent loses interest in it. However, because state prediction or surprise increases on average by increasing the stochasticity, the noisy TV remains always attractive for surprise-seeking agents. So this exercise is supposed to give you some intuition that why information gain seeking is better than surprise seeking in the presence of stochasticity. But then the question is that how one can efficiently implement a similar reward signal in deep reinforcement learning to deal with the noisy TV problem. And this is the third example that we discuss for the intrinsic motivation in deep reinforcement learning. The first one was for novelty seeking. The second one was for surprise seeking. And the third one is for a measure similar to information gain. The measure is called Disagreement. It is proposed by Pathak and colleague in ICML 2019. It is one of the state-of-the-art intrinsic motivation. It has some very cool application that you can see in these two other more recent papers. I really recommend looking at these papers. They're amazing. They show all the benefits and exploit all the capacity of these intrinsic motivations. To discuss what is disagreement and how it is computed, I'm going to show you the block diagram of the model used by the authors and discuss it elements by elements. So here we have the current observation. It is received, shown by xt. It is received by the agent or policy network. Based on this current observation, the agent make an action, and this action has some consequences, which is xt plus 1 is the next observation. And now the next observation is received by the agent. Here we see how the disagreement and the intrinsic reward is computed. If you remember, in the surprise seeking, the agent was making some forward models to always predict the next observation. Here the agent, instead of one forward model, has n different forward models. Each of these forward models receive xt and at, which is the current observation and current action, and predict the next observation. Importantly, these different forward models are randomly initialized and are trained with bootstrap samples. So in that sense, they have different prediction more or less. For example, in this case, you had this bottle on the table. The action was to push it. The true observation is that it falls on the table. However, for example, model 1 can be correct to say that, okay, it falls. This one can say that it just moves, and this one can say that it doesn't move at all, and it remains as it is. And now, the agent use these predictions, compare them to xt plus 1, and by doing so, compute n different prediction error, and by minimizing them, train these forward models. So the error is used for training the forward models. But intrinsic reward or disagreement is defined as variance of the predictions of these different n forward model. So the more different the n model, the higher the intrinsic reward. Importantly, as you see in the exercise 2 of Week 13 in a simple setting, this variance converges to 0 in the limit of t to infinity. It's similar, and because of this, it is a bit similar to the information gain. More intuitively, to discuss about this, you can consider the more agents interact with parts of environments, the more these n different forward models get trained, and their prediction get more and more accurate and similar to each other. So their variance decrease. But the variance is big for the part of the environment that the agent hasn't interacted with very often, and the forward models are not trained very well there. So if you consider the example of noisy TV, if the agent stay in front of the noisy TV for a long time, it's true that the agent cannot predict anything, but all of these forward models go to a converge to a model that predicts the average image of the TV. So the variance finally goes down, no matter how stochastic the TV is. And that's what the authors show by unity maze. They mean exactly the same case that I showed in the 2 slides ago. Same navigation task here without TV, and here with TV. And as you can see, the blue curve is the surprise seeking of Burda et al. In ICLR 2019, and the green curve is disagreement. And as you can see, disagreement and surprise seeking both work well in the case of no TV and without stochasticity, but as soon as the TV and stochasticity is added, there is a big difference between surprise seeking and disagreement seeking. And disagreement seeking beats surprise seeking by a big margin. One puzzling thing for me when I saw this curve in the paper of Pathak et al. In 2019 was that the curve for surprise seeking is very different compared to the original paper of Burda et al. As you can see here, as soon as the TV is added, surprise seeking totally fails in the original paper, while in the other paper, in the new paper, in the paper of Pathak et al., surprise seeking still can work decently. I could not find the supplementary material for the disagreement paper, but what I understood is that in the paper of Burda et al., they try to scale the reward signal to have a similar scaling of intrinsic reward, surprise, and extrinsic reward, the reward of the task. And because of that, there are lots of weights on the surprise seeking. And my guess is that because of that reason, this drop is so big. While here, my guess and my understanding from the paper is that rescaling is not done. And basically, that is also another evidence for that is that around 9 million frame of training, which is here, in the absence of reward, still surprise seeking is around 0.5, while here surprise seeking is around 0.8. And I guess the main difference between the two simulations is based on the value of surprise in two different models, which results here we have a slower learning because the value of surprise is lower, and the agent does more random exploration, and here we learn faster because value of surprise is higher, and the agents follow surprise and more directed exploration. But on the other hand, because of the same reason, here we have a more catastrophic consequence of surprise seeking in the presence of stochasticity, while here the difference is not as big as the original paper. But this is just the detail. The important message is that disagreement is a simple intrinsic reward, easily implementable in deep reinforcement learning, and can solve the noisy TV problem to some extent. So far we saw that being curious in the presence of stochasticity can result in the noisy TV problem and agents getting distracted by the unstructured stochasticity. We saw how noisy TV problem can be addressed in deep reinforcement learning by using disagreement. And in the next section, we are going to focus on human participants and see if they also get distracted by stochasticity or not. So far, we observed that different intrinsic rewards result in different levels of distraction by stochasticity. An important question that one can ask is whether human participants also get attracted to unstructured stochasticity, and if they do so, which intrinsic reward signal explain their behavior best. This is a question that we try to address in this preprint on bioRxiv, where our methodology is to first design an experimental paradigm where attraction to unstructured stochasticity is observable and is possible, and also different intrinsic reward signal make different prediction for human behavior. And after designing that, comparing the behavior of human participants and different algorithms in the same experimental paradigm. For the experimental paradigm, we consider this simplified environment with 58 states and 3 actions per state, which has a section similar to a noisy TV. The environment, except for the part that is similar to the noisy TV, is very similar to the environment that you saw in the class on novelty seeking in humans and the exercise that you had in week 12. The environment has 6 states here that we call progressing states, 1 goal state, and 2 trap states. When the agent is in this progressing state, there's always 1 action can take agent closer to the goal state, 1 action that take agents to trap states, and 1 self-looping action except for state 4. When the agents go to the trap states, then 2 actions keep them in the trap states and 1 action let them go out of the trap state into state 1 to start from scratch and get closer to the goal states. When they are in state 4, they can go to this stochastic part, which we called TV-like part. And when they take this action here in state 4, they go with uniform probability to one of these 50 stochastic states. And when they are in one of these 50 stochastic states, 1 action always take them out of the stochastic part to state 4. So it is not possible for them to get lost in this stochastic section, but there are also 2 actions that if they take, they are randomly taken to another stochastic state. So in this sense, it is very similar to the noisy TV of Burda et al. Importantly, neither human participants nor artificial participants or RL agents are aware of the total number of states in this environment. So they don't know how many states are out there. This is a bit different from the settings that what you have seen so far. I'm not going to discuss about it, but you can check the detail, the mathematical detail of the algorithm in the paper. For human participants, we asked 21 participants to play in this task for 5 episodes, meaning that they should find the goal state 5 times. In the experiment, they sit in front of a computer. At each time, they see 1 image on the computer screen, which corresponds to one of states, one of the disks here. Then they observe 3 disks below the image, which corresponds to the different actions. and if they select one of these actions by clicking on the disk, they are moved to another state and they see another image. And they are instructed to keep taking actions until they found the goal state, which is a thumb here. To motivate exploration in the humans and study how they explore the environment, we tell them in the instruction that there are 3 goal states in the environment. So we tell them that if for the goal state they found this image, if they see this image, they receive at the end of the experiment 2 Swiss francs. If they see this image, they receive 3 Swiss francs, and if they see this image, they receive 4 Swiss francs. However, for this 21 group of participants, there is only one goal state with the lowest value of reward, with 2 Swiss francs. So at the end of episode 1, when the agents get here, they observe this image, they see that, okay, they get 2 Swiss francs, but they are aware that there are 2 other goal states in the environment, and this gives them some monetary incentive for exploration in episodes after episode 1. For the algorithm, what we do is to have these RL agents that receive a state st. There is the reward function module that compute intrinsic reward and extrinsic reward. Intrinsic and extrinsic reward are processed in parallel in 2 RL algorithms. They are identical except for their reward signal. One gives us one purely intrinsically motivated policy, and the other one purely extrinsically motivated policy. And the goal of us, or goal to separate the 2 policy was to have one policy for exploration and one policy for exploitation. We show that this is necessary to explain the behavior of human participants. The 2 policies are then combined in the action selection by some free parameters that put weights on the exploration versus exploitation, and the agent takes this action. The action is passed to the environment, which is same as the environments that are used for human participants, and the next state is taken from the environment, and we go forward. We consider 3 options for the intrinsic reward here, and these 3 options, one is the Shannon surprise, one is novelty, and the other one is information gain, but the one based on Kullback-Leibler divergence. As we discussed before, we have this order for how good different algorithms are for dealing with stochasticity. We know that information gain is better than novelty, and novelty is better than surprise seeking. Now we have the experimental paradigm. When we have the algorithm to run them in this experimental paradigm, and we have human participants to ask them to do the experiment, and we can compare the behavior of the 2. So let's consider episode 2 to 5. At the end of episode 1, the agent has found the 2 Swiss franc goal state here, but it knows that there are better goal states out there. And our question is that how the agents search for these better goal states. Let's first look at the predictions of different intrinsically motivated algorithms and get some insights about different exploration strategy before we collect data. So this is only theoretical. It's for perfect model-based agent for pure exploration. So the agent does not care about the reward of these, the small reward of these 2 Swiss franc goal state, and only follows intrinsic motivation to explore the environment. The first option is surprise seeking. Here on the x-axis you see number of episodes. So in episode 1 the agent found the goal state once. In episode 2 it found it for the 2nd time, 3rd time, 4th time, and 5th time. On the y-axis you see the number of actions that the agent takes at each point. The bars show the median number of actions, and each of these dots is one of the simulations. 3000 step is where I kill the simulations because otherwise it can run forever. As you can see, the number of actions is very high. The agents get distracted by stochastic state to the extent that in episode 5, 53% of simulations spend more than 3000 steps in the stochastic part of the environment and they don't find the goal states. While we still see an increasing pattern for the novelty seeking, but the numbers are much, much smaller than the numbers for surprise seeking. And this is consistent with our expectation for novelty seeking compared to surprise seeking. So novelty seeking still shows some degrees of distraction by stochasticity, but it is not as harmful as surprise seeking. But if we look at the information gain seeking, as expected from the theory, we see that at the beginning it spends some good amount of time in the stochastic part, but this decreases over time, seen by a negative correlation. So information gain seeking after a while realized that there's no information in the stochastic part, in the TV-like part, and it started avoiding it even if it is not motivated by extrinsic reward, while novelty and surprise are keep being attracted to it to the extent that surprise seeking most of the time gets stuck there. Now we can look at human participants, collect data and analyze these data. Human participants spend very less time than surprise seeking, but importantly, what we observe for the correlation of number of actions in the episode, we see a kind of a flat line here. The flat line is the zero correlation is accepted by Bayesian hypothesis testing, showing that human participants show a persistent distraction by novelty. So it doesn't go down like information gain, and it doesn't go up like novelty and surprise. If then we try to modify this perfect model-based algorithm and make them more realistic to fit the behavior of human participant, so have a hybrid reinforcement learning, a combination of model-based and model-free, we allow the agent to have leaky memory. So we allow the agent to forget things, don't have a perfect memory like humans actually. And we allow for balanced exploration. It's not pure exploration anymore. The agent puts some weight on this 2 Swiss francs and say that, okay, it's true. I know that these better goal state exist, but there's still some reward value on this, and the agent should not ignore that. If we do that and then fit this model to the behavioral data, we observe that this is on the y-axis, you see the expected posterior probability of each model is the probability that each of these models has generated data. And we see novelty seeking outperform the other models in explaining human behavior. Particularly this number here, PXP, is protected exceedance probability, showing that with what probability novelty seeking is dominant. And we see that it is almost with probability 97% better than the other two. And if we keep this novelty seeking, the fitted novelty seeking, and simulate it, we see the exactly same numbers and exactly same correlation as we saw for human participants. So it seems like that humans are not as efficient as information gain, but they are not as bad as surprise seeking. And they are somewhere in between for novelty seeking. And novelty seeking can explain all aspects of their behavior. You can check other statistics in the preprint, but here I just discussed about number of actions. So we design an environment, we design an experimental paradigm where distraction by unstructured stochasticity was observable, and then we compare the behavior of human participants with the algorithms. Now we can answer our question. Do humans also get attracted to unstructured stochasticity? Yes. And which intrinsic reward signal explained their behavior best? The answer that we found was novelty. Before finishing the lecture, let's discuss about the other reward groups. So before I said that we asked human participants to play for 5 episodes in this environment, and we had told them that there are 3 goal states, one with 2 Swiss franc value, one with 3 Swiss franc value, and one with 4 Swiss franc value. And there were only, for these 21 participants that so far I showed their data, there were only 1 goal state with 2 Swiss franc. Actually, we could do the same thing, having only 1 goal state in the environment, but this 1 goal state could be 3 Swiss franc or 4 Swiss franc. And in this way, we could add a dimension, add a variable between different participants that we could call, and we call, reward optimism, that if the participants find this 2 Swiss franc at the end of episode 1, they have a high reward optimism in episodes 2 to 5, because they know how they can find the 2 Swiss franc, but they're aware that there are much better goal states out there that they can go and search for. But if the participants find the 4 Swiss franc reward at the end of episode 1, during episode 2 to 5, they have very low reward optimism, in the sense that they know that they cannot find anything better than this 4 Swiss franc that they already know where it is by exploring. So we wonder how people would react and behave in our experiments if we show them these rewards. And this is actually the precise experimental procedure that we had. We invited participants to the lab and assigned them randomly to these 3 reward groups. 21 participants went to the 2 Swiss franc group, 19 went to the 3 Swiss franc group, and 17 to the 4 Swiss franc group. And now I'm going to show you in the next slide the behavior of these different groups. So here on the x-axis, you see the reward optimism, different groups of participants, the 4 Swiss franc, 3 Swiss franc, and 2 Swiss franc. On the y-axis, you see the fraction of time that people spend during episode 2 to 5 in the stochastic part of the environment. And as expected, as we increase reward optimism, people spend more and more time in the stochastic part of the environment. So it seems like that increasing, the more optimistic people are about finding a better goal state, the more likely it is that they go to the TV-like part and get distracted by stochasticity. We can look at our model after fitting it to the behavior of human participants and analyze the importance, the influence of the intrinsic motivated policy and extrinsic motivated policy on action selection, and compute a relative value for novelty, that how much novelty influences behavior, and look at it as a function of reward optimism. What we observe after fitting the model to behavior is that the value of novelty increases by increasing reward optimism. So reward optimism influences the behavior of human participants in some sense by increasing the value of novelty and increasing the value of exploration. If now we simulate these fitted models, we see exactly the same pattern of behavior for the simulated participants as we saw for the human participants. And by this, what I want to conclude is actually what we see about distraction by stochasticity and noisy TV problem is not only about the reward signal and intrinsic motivation, but also about the value of that intrinsic motivation. As we saw in the comparison of original paper of Burda et al. And the using surprise seeking of Burda et al. In the paper of Pathak et al. 2019, decreasing the value of surprise seeking stopped the catastrophic consequence of surprise seeking in the presence of the noisy TV. And here we see a similar thing, that if we decrease the value of novelty, the agent spends much less time in the stochastic part of the environment. So before finishing the lecture, it's time for quiz of part 3. The first question: seeking surprise is more prone to noisy TV problem than seeking information gain or disagreement. The statement is correct. We saw it both based on some theory insight in the exercise and by looking at the empirical results of different papers, that surprise seeking is more prone to the noisy TV problem. Second statement: disagreement is an exact implementation of information gain for high-dimensional state spaces. This is incorrect, because disagreement measures only the uncertainty in the agent's world model, or the difference between different forward models of the agent, while information gain compute the gain and changes in this forward model by each transition. The two are correlated, and the two converges to 0 as time passes on, but they are not the same. The third statement: humans are also prone to the noisy TV problem. And I would answer yes. And how prone they are to the noisy TV problem depends on how optimistic they are about finding better rewards in the environment. And finally, humans seek novelty to explore their environments. The statement, I would say, is neither right or wrong. The reason is that so far we saw in some situations that novelty seeking is a better explanation for human behavior. And we see humans behave as if they are seeking novelty. But we cannot be sure. We can never be sure because there are many different scenarios that our models are not considering. And it's just too much of a big claim to say that humans seek novelty. But in some scenarios, we can be confident that the behavior can be explained better by novelty seeking than surprise seeking or information gain seeking. So to summarize the third part and the last part of the lecture, we got introduced to the noisy TV problem, which is the problem of a curious agent getting distracted by unstructured stochasticity. We saw that the degree of distraction is different for different intrinsic rewards. Surprise seeking was worse, while information gain seeking was best, and novelty seeking something in between. We observed that over-optimism increases the influence of novelty on human exploration and makes them prone to the noisy TV problem. Then we saw that the distraction by stochasticity in humans is explained best by seeking novelty compared to seeking surprise or information gain. And finally, we can make a conclusion based on these two facts that algorithms that are good in solving a task are not necessarily good in explaining human behavior in the same task. And by this, I would like to finish this lecture and go to the overview. In the part 1, we discussed exploration bonus in tabular reinforcement learning and how it can help collecting reward in multi-unbounded task and Markov decision processes. Then we discussed the benefits of curiosity-driven reinforcement learning and intrinsic motivation in deep reinforcement learning and in the situation without reward. And finally, we discussed the problems of these methods when there is stochasticity, when there is a stochasticity in the environment. And we compared the behavior of these models with the behavior of human participants in similar tasks. And this is the end of our lecture on curiosity-driven exploration. I hope you have enjoyed it.